In this class, we will study the forced vibrations of a 2 degree of freedom system. We have here an example of a 2 degree of freedom system, two masses fixed with three springs, and the forcing function is acting, F cos omega t is acting on one of the masses. As I was mentioning earlier, the main difference between a forced vibration system and a free vibration system is that in the case of forced vibration, the whole of the system will be vibrating at the frequency of the forcing function. In this particular case, it is omega. In the case of free vibrations, under certain initial conditions, the whole system will be vibrating at one of the natural frequencies. Whereas in the case of forced vibration, it will be vibrating only at the forcing frequency omega. What will be of interest for us to study will be the amplitudes of vibration of masses m1 and m2 as we change the frequency from omega from a low frequency to a very high value, covering of course the two natural frequencies also. Well, to study, as you know, the two equations of motion as we have seen in the case of free vibrations are these two. After a slight initial modification, one difference is you find f here in the place of 0, which you had in the case of free vibrations. Now let us assume this mass m1 is going to oscillate at x1 is equal to a1 cos omega t, and the motion of x2 is given by x2 is a2 cos omega t, where a1 and a2 are the two amplitudes. Well, these are the two governing equations. Solving these two equations, we will get the amplitude a1 given by f into k2 plus k3 minus m2 omega square divided by k1 plus k2 plus m1 omega square into k2 plus k3 minus m2 omega square minus k2 square. Similarly, for a2, you have fk2 divided by the same denominator as per a1. Well, the amplitudes naturally a1 and a2 will reach theoretically infinity when you get when the frequency omega reaches the natural frequency. That is the case of resonance. Well, for that to happen, we have to have this denominator becoming 0. Well, when this equation, the denominator being made equal to 0, that equation results in, after some manipulation, it will result in this frequency equation, omega 4 minus k1 plus k2 by m1 plus k2 plus k3 by m2 into omega square plus k1 k2 plus k2 k3 plus k3 k1 by m1 m2 equal to 0. This is the frequency equation, and this is the same thing as in the case of our free vibrations. Well, solving this equation, taking the two positive values, we will get omega 1 and omega 2, which are the two natural frequencies. Well, we will take one simple example where the masses m1 and m2 are both equal to m, and the three spring stiffnesses are all equal to k. In this particular case, as we have seen earlier, the frequency equation reduces to this form, from which you get omega 1 to be root k by m, the first frequency or the fundamental frequency, and the second natural frequency omega 2 is root 3k by m. Well, when you substitute this value of omega 1 in the omega that you get from the amplitude, from the previous amplitude equation a1, once you substitute k1 equal to k2 equal to k3 equal to k and m1 m2 being both equal to m, this is the reduced form for the amplitude a1, and this once you divide f divided by k, and then you further reduce a1 by a1 as a1 over f by k, what you get here on the right hand side will be 2 minus r square over r square minus 1 into r square minus 3, where r is the ratio of the forcing frequency to the natural frequency. That is, r is equal to omega over omega 1. On the, as I was telling, you will be studying the amplitudes of the two masses as a function of the frequency omega. are actually we're going to study it as a function of the ratio of the frequency to one of the natural frequencies. In this particular case, when I take f1, the omega 1 to be root k by m, I will be getting uh, curves of this form. That is, I have drawn a1 over f by k on the y-axis. That I have represented the value as I keep changing omega on the x-axis or r on the x-axis. You will find that when the when r becomes equal to 1 or r is equal to root 3, you will find that the denominator becomes infinity. Naturally, these two happen to be the two natural frequencies, and under those situations, you will find that both the amplitudes a1 and a2 represented by the dotted lines, they both reach infinity, and that happens at r equal to 1 and also r equal to root 3 corresponding to this equation. Corresponding to this equation also, that is the amplitude of the second mass a2 is represented by this, and we find that r equal to 1 and r equal to root 3, you will get the the amplitude a2 also going to infinity, represented by the dotted lines. You will also find that when r is equal to root 2, the amplitude a1 becomes 0. That is what you see at this point. When r is equal to root 2, the amplitude a1 becomes 0, but a2 would have a finite value given by whatever it is. Well, that is the complete representation of the uh, variation of the amplitudes of the two masses as a function of the frequency of the forcing function, represented of course as a ratio to the one of the natural frequencies. You get a similar graph when you use omega 1 when you replace omega 1 by omega 2. Well, again, when r reaches a value, a very high value, you will find, but in both the expressions, the denominator takes on a very high value. Naturally, the two amplitudes will become close to 0. That is what you see here. Well, that completes the uh, our topic of uh, forced vibrations, in which we basically study the variation of the amplitudes of the two masses as we change the frequency. Thank you. Uh, uh.